Hi there everyone, my name is Sashan. I'm currently an MSc student and I'll be talking to you all about biogeochemical feedbacks. So within our hierarchy of models, we've progressed quite a bit. We began by looking at the Earth as a bare rock where we found it to be too hot. By adding a static atmosphere and ocean, we found that the Earth was too cold. By enabling atmospheric and oceanic circulation to take place and continue, we improved conditions somewhat, and with the advent of plate tectonics, enabled further progress in enabling Earth to become habitable. With enough time and trial and error, we found that life began to evolve. At this point, we're at the fifth model within our hierarchy, where life is present, and the biosphere is interacting with all the other components of the Earth, so the lithosphere, the atmosphere, and the hydrosphere. All of these different spheres of the Earth are interacting with one another, with the processes from these different spheres feeding back into one another, amplifying and inhibiting their processes. And we'll explore this further. To do this, we'll first lay a foundation with a couple of definitions, namely definitions of what life is and defining what feedback is. Then we'll move on to exploring this idea or hypothesis of Gaia, which was first proposed by the British scientist James Lovelock. This hypothesis basically explores the idea that life affects its environment as much as it is affected by its environment. Conventionally, we understand that any life form which exists tends to be influenced by the environment in which it inhabits. However, as we'll see, life can also affect or influence its environment. Then we'll move on to the daisy wheel model, which was a model first proposed by Lovelock as well, to explore or test rather the existence of Gaia. From there, we'll move on to exploring a couple of case studies of biogeochemical feedbacks, which operates in the real world on a day-to-day basis. So we'll define life according to Cleveland's definition, that is, it being any self-sustaining chemical system that is capable of undergoing Darwinian evolution. And it should have the parameters which we would normally use when defining life, that is, by its ability to reproduce, grow, move, engage in respiration, etc. By this definition, we'll therefore have to exclude mules or viruses, among other things. So feedback can be any mechanism that can control a process or system by its cause or effect. You get different types of feedbacks, namely positive feedbacks and negative feedbacks. Positive feedbacks are those mechanisms which result in the growth or amplification of a system or process, whereas a negative feedback is a mechanism that results in the inhibition or slowing down of the system. It is important to note that positive feedbacks are not necessarily good. Likewise, negative feedbacks are not necessarily bad. Additionally, feedbacks tend to be non-linear systems. They can be cyclical if they're allowed to continue without interruption. And it's also important to note that any small changes in the causes of whatever effect takes place can result in the effect being disproportionately larger. So an example of a positive feedback can be, the Industrial Revolution, where after conducting, scientific research or research of any form, we have an initial breakthrough. This enables us to have an advancement in technology, which allows us to create more tools. With more tools, we can engage in more intensive research and innovation, and by continuing that, we may be able to make new breakthroughs. New breakthroughs will allow us to advance our technology even more, which then will enable us to create even more tools, more advanced tools, which can allow us to engage in even more advanced and intensive research and innovation, enabling more breakthroughs to take place, and so on. An example of a negative feedback could be how we regulate body temperature. So say our body is at some sort of equilibrium. If our body temperature were to decrease a bit and then decrease too much, we would begin to feel cold, and our body would respond to that by shivering to generate heat. As we begin to generate heat, our body temperature begins to increase. It'll reach a point of equilibrium, or it equilibrates rather, and if it continues to increase, our body temperatures could increase too much. As a result, we may begin to sweat to cool our body temperature down. And then as we sweat, our body temperature decreases until we reach another point of equilibrium. And if that remains unchecked, our body temperature can decrease too much And so we can see how the cycle continues from that point. So where to from here? Well, we can have a brief exposure to Gaia. So the Gaia hypothesis was first proposed by James Lovelock, who was a British scientist in the 1960s. He wrote extensively about Gaia in the decades subsequent to that, most notably in his book, Gaia, A New Look at Life on Earth. So Lovelock considered Gaia to be a complex entity made up of all the different spheres on Earth. So Gaia was comprised of the biosphere, the atmosphere, the hydrosphere, the lithosphere, etc. that worked in conjunction and worked together to try and seek out an optimal environmental condition on the Earth to enable life to flourish. He forwarded the notion that Gaia modified the conditions of the environment, notably the atmosphere, to enable the Earth to be more habitable for life to evolve and flourish. But when you think about it, it does sound a bit ludicrous, because how can life control its environment to allow it to survive and to flourish? Normally the conditions of the environment need to be as such where life can flourish from that point. But to look at that, we need to take a peek at our atmosphere. We can see that it's made up of a variety of different gases. I've indicated some in red to illustrate that the importance of the different gases of our atmosphere is not determined by their abundance. The ones in red are those gases which are inert. And if we were to remove those, we'll be left with the ones illustrated in this graph below. And we can see that these gases are the ones which are chemically active. And in addition to that, they're also the ones which are produced or regulated in some way by biological life. Furthermore, I suppose, is to indicate that some of these gases are also greenhouse gases. To look a little bit further at specific gases, if we look at temperature and carbon dioxide, which are illustrated on this graph, where we have time on our x-axis and temperature and carbon dioxide content on our y-axis, we can see a clear relationship between temperature and carbon dioxide. Namely, that as you increase your carbon dioxide content in the atmosphere, we also increase our temperatures. So we can extend our understanding that if biological life regulates the content of carbon dioxide in our atmosphere, and if carbon dioxide influences the temperatures of our planet, then we can extrapolate and say that biological life also influences our temperatures. So to take this point further, we can look at how life is involved in regulating and cycling carbon. When we look at the carbon cycle, we can see that carbon and carbon dioxide can be circulated among biological life through photosynthetic and respiratory processes, and terrestrial life, for example. In aquatic life, I suppose, we can see that carbon can be stored and locked away when various forms of aquatic life die, and they store carbon in their skeletal structures, which collects on the sea floor. To look at, say, the water cycle, we can see how water is circulated, controlled, and regulated by life as well through various evapotranspiration processes. And if we were to look more closely at processes that biological life involves, and we can take the process of photosynthesis engaged in by flora, which regulates the presence of water, carbon dioxide, and oxygen. So what does all this tell us? What does it tell us about Gaia? Well, to Lovelock, he notes that in spite of solar installation having increased by up to 30% over the last couple of decades, we've noticed that temperatures have not. And why? Why is that? He further observed that in spite of the atmosphere having so many chemically active species, its composition has remained relatively constant. Why? Furthermore, he noticed that oceanic salinity has remained relatively constant as well, in spite of it being known that biological and organic processes operate within, ocean water constantly. So what does this tell us? Well, to Lovelock, it reinforces the idea and the existence of Gaia, because it suggests that life is controlling the conditions of the planet to enable itself, or to enable life to flourish. Life is controlling temperatures and keeping it at in a habitable range so that life can continue to exist. It maintains the atmospheric composition so that it can continue to exist and flourish as well. Likewise with salinity content. In fact, when exploring for life on other planets, Lovelock suggested that instead of looking at the lithosphere for fossils or other ancient remnants of life, we should be looking at the atmosphere. However, as with any scientific theory or hypothesis proposed, it will also be met with criticism. And some of the criticism is that there is no direct evidence or observation for Gaia. In fact, Gaia is quite difficult to test for. Critics have said that the Gaia hypothesis is teleological, meaning that on the grounds of the observations that Lovelock made, he has just claimed that therefore, because the conditions are such, Gaia must exist, even though he has provided no evidence for it. In addition, as Lovelock describes or defines Gaia as being a living entity comprising the different spheres of the Earth which interact in conjunction together to modify the conditions of the planet to enable it to be habitable, it doesn't really line up well with Cleveland's definition, because if Gaia is a living entity, and if the Earth is alive by extension, that means it is able to reproduce, but the Earth can't reproduce to form another Earth. However, Lovelock did come up with an idea, a model to test for Gaia, which is the daisy world model. It is, you can say, a bit of an extension of our barren rock model, where instead of just having a barren rock, we now have colorful daisies which inhabit it. And these daisies are able to grow based on the amount of solar insolation that they receive. The model was established to show or test or illustrate how life could survive on the Earth by regulating its temperature, and to Lovelock how it could justify the presence of Gaia. So on Daisy World, our black daisies will create areas of low albedo and can cause local areas of warming. Our white daisies will have a relatively higher albedo and can cause localized areas of cooling. Both daisies grow within a minimum and maximum temperature range and can't grow if it gets too hot or too cold. So if we were to consider the sun that lights daisy world to get hotter, what would happen? Let us take a look at this graph. So this graph shows temperature on the y-axis and time on the x-axis, with arbitrary temperatures and times and arbitrary minimum and maximum temperatures. We have black dots, which represent clusters of black daisies, and red dots, which represent clusters of white daisies. So at a minimum temperature, we can see that the black daisies and the white daisies begin to grow. The local clusters of black daisies are relatively warmer than those of the white daisies. So as they begin to grow, the clusters of black daisies will create a net warming effect on the Earth, gradually raising the temperatures of the Earth. And you can see those clusters of black daisies begin to get warmer. Likewise with the white daisies, but which are relatively cooler than the black daisies. When the black daisy's temperature exceeds the maximum temperature threshold, they begin to die. Whereas when the white daisies, which are still growing, may be within the maximum temperature threshold, they may continue to live and continue to grow. As those clusters of white daisies continue to grow, their lower albedo can result in there being a net cooling of the Earth, and as you can see, temperatures will begin to drop until it falls within the maximum temperature range again, and we can see that the black daisies begin to grow again, until a point is reached where the net cooling effect of the white daisies results in temperatures dropping too much until it drops below the minimum temperature range, where it's now too cold for the white daisies to grow, whereas the temperatures of the black daisies may be slightly warmer and within the minimum temperature range. And so as the white daisies begin to die, the black daisies will begin to grow from there. If we were to look at this next graph, which shows area on our y-axis and time on our x-axis with our minimum and maximum temperatures superimposed, we can see how the area of coverage of our white daisies and black daisies is illustrated. We can see that as temperatures increase, the area that the black daisies cover increases until the maximum temperature is reached, when it is too hot for them to grow until they die. And we can see as temperatures begin to decrease, the white daisies have a much larger aerial coverage until temperatures drop too much, and then it is too cold for them to grow, so they begin to die, and the black daisies begin to grow, and then they begin to cover a much broader area. This continues for what seems for an indefinite period and illustrates how life on the planet controls the conditions on the planet which enables it to flourish. And I suppose it does show how life could thrive this way. It shows the role that feedback plays in influencing processes and in driving systems, in this case showing how life can continue to thrive. If we were to look at a couple real-world known examples of biogeochemical feedback, we can look at, for example, temperature changes, where we can have some sort of initial change that can cause a general cooling of the Earth or net cooling of the Earth. This can result in there being an increase in ice growth. An increase in ice growth can cause an increase in global albedo. With an increase in global albedo, there'll be less insolation or solar insolation, which therefore can drive even more cooling, and so on and so forth, which will drive more ice growth, a further increase in albedo, and even less insolation being absorbed. In an opposite sense, rather than having general cooling, we can have a general warming effect. And this, as you can see, in either situation, if either of these are allowed to continue unchecked, it can be disastrous. It is, I suppose, a good example of how, even though these are positive feedback mechanisms, they aren't good at all for the planet and especially for people and various forms of life. The importance of this sort of feedback is illustrated in a lot of research that has been conducted in recent times. So these are just a couple of papers that have been published during 2020 about ice sheet melt in Greenland and the relationship of this melting of the ice sheets to temperature changes as well as to sea level rise. An example of a negative feedback can be chemical weathering. Through the combination of carbon dioxide with rainwater to produce carbonic acid, this can react to break down a whole variety of minerals within the Earth's crust, such as carbonates like calcites and silicate minerals like feldspars. These can be broken down to produce things like clays, and you can dissolve carbonates as well. The importance of that is that when you have increased chemical weathering, especially in the tropics, it can have some temperature implications. So if you were to have an increase in general warming, you can see an increase in weathering, which can remove carbon dioxide from the atmosphere, which can drive a weaker greenhouse effect and can cause a net cooling. With there being a net cooling, there could be a decrease in chemical weathering, enabling carbon dioxide, for example, to accumulate back into the atmosphere. With carbon dioxide accumulating back in the atmosphere, there could be a stronger greenhouse effect, which can drive a net warming of the planet. Processes like this operate globally, and so South Africa, it being in the tropics, is involved in these sorts of processes, and we should be cognizant of that. In summary, we can understand that organisms and biological life do have a role to play in regulating the presence of carbon dioxide, oxygen, and water vapor in our atmosphere and within the broader cycles themselves. We also know that life and the various components of the Earth, in terms of the lithosphere, atmosphere, hydrosphere, are all interlinked and they all are related to one another. The significance of Gaia is that Gaia illustrates the importance of considering all the different facets of the Earth in trying to understand its story and in trying to understand the bigger picture of what it is that relates to the Earth and its habitability. In our next lecture, we'll look at the story of humans, how we evolved from our earliest ancestor up until where we are now. So stay tuned.